In Part 3 of Lecture 2, we will discuss multiprogramming. Even with the automatic job sequencing provided by a simple batch operating system, the processor is often idle. The problem is that input-output devices are slow compared to the processor. The slide details a representative calculation. The calculation concerns a program that processes a file of records and performs, on average, 100 machine instructions per record. In this example, you can see that we spend all of 1 microsecond executing all 100 instructions, yet we spend 15 microseconds each on reading a single record and another 15 microseconds for writing a single record. That means the computer spends over 96% of its time waiting for input-output devices to finish transferring data to and from the file. The illustration on the slide illustrates this situation, where we have a single program referred to as uniprogramming. The processor spends a certain amount of time executing until it reaches an input-output instruction. Then it must wait until that input-output instruction concludes before it can proceed. This inefficiency is not necessary. We know that there must be enough memory to hold the operating system, in other words, the resident monitor, and one user program. Suppose there is room for the operating system and 2 user programs. When one job needs to wait for input-output, the processor can switch to the other job, which is likely not waiting for input-output. Furthermore, we might expand memory to hold 3, 4, or more programs, and switch among all of them, as is illustrated in the figure. The approach is known as multiprogramming or multitasking. It is the central theme of modern operating systems. To illustrate the benefit of multiprogramming, we give a simple example. Consider a computer with 250 megabytes of available memory not used by the operating system, a disk, a terminal, and a printer. The 3 programs, Job 1, Job 2, and Job 3, are submitted for execution at the same time with the attributes shown in the table on the slide. We assume minimal processor requirements for Job 2 and Job 3, and continuous disk and printer use by Job 3. For a simple batch environment, these jobs will be executed in sequence. Thus, Job 1 completes in 5 minutes, Job 2 must wait until the 5 minutes are over, and then completes 15 minutes after that. Job 3 begins after 20 minutes and completes at 30 minutes from the time it was initially submitted. Device-by-device utilization is in the left-hand side of the slide. It is evident that there is gross underutilization for all resources when averaged over the required 30-minute time period. Now suppose that the jobs are run concurrently under a multi-programming operating system. Because there is little resource contention between the jobs, all 3 can run in nearly minimum time while coexisting with the others in the computer, assuming that Job 2 and Job 3 are allotted enough processor time to keep their input and output operations active. Job 1 will still require 5 minutes to complete. But at the end of that time, Job 2 will be 1/3 finished, and Job 3 half finished. All 3 jobs will have finished within 15 minutes. The improvement is evident when examining the multi-programming column of the table from the previous slide, obtained from the histogram shown on the right-hand side of this figure.